right, so now that we've talked about atoms, we're going to move specifically into electrons. And before we can really explain electrons, we need to diverge a little bit and talk a little bit about light. Now, the reason that we're doing that is because light has properties of waves and particles, and it turns out that electrons also have properties of waves and particles. So understanding the behavior of light will help us to understand the behavior of electrons as well. And so that's what we're going to be talking about in this section of the chapter. So first thing we're going to do is some basic definitions. So talking about waves specifically. So wavelength, this is the Greek letter lambda. You definitely need to know the symbol for wavelength. Know that it stands for wavelength. We're actually going to provide for you the formulas that you'll be learning on the test. But we're not going to tell you what the variables stand for. So we want you to make sure you understand, oh, that Greek letter looks kind of like an upside down Y. That's the symbol for wavelength. You also need to know how these different units are measured. So wavelength is measured typically in meters. Sometimes it's nanometers, and we'll talk about that. We might change the metric prefix depending on what we're measuring, because maybe it's something that would have a very large or very, very small wavelength in just meters. But meters is the standard unit that we're going to use. So a wavelength is usually measured crest to crest, the crest being the top of a wave, but technically a full wave, just to clarify, would be this, starting here at the origin. It would have one crest, one trough, and then it would end here. So another way you could also measure wavelength would be from origin to origin here, but commonly it's crest to crest, or it could also be trough to trough. So that's our wavelength. Next is what's called amplitude. So amplitude, if you were thinking about sound like an amplifier, this would be basically raising the amplitude would make it louder, or if it's a light and you had it on a dimmer switch, if you raise that dimmer switch and make the light brighter, you would be changing the amplitude of the wave. And the thing with amplitude is that it doesn't change the wavelength. In other words, if I just did this, and this was, say, a wave that was a sound wave, notice the wavelength is the same, but now I've increased the amplitude. So this might be a louder sound or a brighter light, depending on what the actual wavelength of this was. And so that's amplitude. And then last is frequency. So frequency, this looks like a letter V. It's actually Greek letter nu. And it is the number of wave cycles per unit of time. So it's usually waves per second, which would be written like this, seconds to the -1. Or it can also be measured in hertz. So if you've ever heard of, for example, AM, FM radio frequencies, 100.7 megahertz, that's because it's the frequency of the waves that are then creating that radio station is broadcasting on. So again, the crest is the top of a wave and the trough is the bottom of a wave. So just to show you again some different waves here. Here you see wavelength. Here you can see the amplitude of this wave. The amplitude of this wave is the same, but the wavelength is shorter. And because the wavelength is shorter, this actually has a higher frequency. And these are actually related to one another. We're going to talk about that. This would have a different amplitude. So this may have the same wavelength as the other two waves, but the amplitude is smaller. So this would be quieter sound, or this would be less dimmer light. So if we were going to compare two waves, so this is two waves and the distance they traveled in 1 second, or how many waves, I should say, passed in 1 second. And so if we look here, we can count how many waves passed in 1 second here. So 1, 2, 3, 4, 5, right? So this wave 1 would have a frequency of 5 hertz. Wave 2, on the other hand, if we look at the wavelength, we see that the wavelength is much shorter. So the frequency is actually going to be higher. We can get more waves per second. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6, 5, 4, 3, 2, 1. And so there we have 10 waves per second, or 10 hertz. Now this can also again be written as 10 seconds to the negative 1. In other words, seconds to the negative 1 is like making it the denominator. So it's basically 10 waves per second is how that would be measured. So how many full waves pass in 1 second? So for wave 1, it was 5 waves. Wave 2 had 10 waves. So for wave 1, the frequency would be 5 waves per second, or 5 hertz. And wave 2 would be 10 hertz. Again, notice the product of these two are actually the same, and as one goes up, the other goes down. And the name for this relationship you've probably learned in math. This is called being inversely proportional. So as one goes up, the other goes down. So there's a formula here. So like we said, the product of these two is actually always the same. It's a constant. Wavelength times frequency always gives us a constant. And that constant is represented by the letter C, and it is the speed of light. And it is measured in meters per second. Now you can also measure it in miles per hour in different ways, but for the purposes of the formulas we'll be using, meters per second is the way that we typically measure this. So it is 3.00 times 10 to the 8th meters per second. Now technically it's actually this. 299,792,458 meters per second. But if we're going to not write out that gigantic number and round it to say 3 sig figs, which is probably going to be the easiest thing to work with, that's why it rounds up to 3.00 times 10 to the 8th. So we can use this formula. If we know the frequency, we can get the wavelength. If we know the wavelength, we can get the frequency. And so because the speed of light is always going to be a constant, we always have one variable. We just need one other one, and then we can do calculations. So some problems that you might be given for something like this. What is the frequency of radiation whose wavelength is 2.40 times 10 to the negative 5th meters? So remember our formula. C is equal to wavelength times frequency. All right, so we have our wavelength, 2.40 times 10 to the negative 5th meters, and we also know our speed of light, right, because that's a constant. So C is equal to 3 times 10 to the 8th meters per second. And so what we're solving for this time is going to be our frequency. Now, my suggestion is to manipulate this formula so that what you're solving for is by itself already before you plug in your numbers. The other thing that some of you guys have been very sloppy about is not including the units in your work. And that's great, except for the fact that when you do that, a lot of times I get people who give me the wrong units in their answer. So if you show your units in your work, that's really the appropriate thing to do, because then we can cancel as we go, and then you'll see what units are left, and you'll know the units for your answer. So it's very logical. You'd also see if you were doing something wrong, because if units aren't canceling appropriately, you probably have a number in the wrong place. All right, so let's manipulate the formula first. So if I'm solving for frequency, I can divide both sides by wavelength, and that's going to get rid of wavelength. And so my manipulated formula would be that the speed of light over the wavelength is going to give me my frequency, right? And so speed of light, 3.00 times 10 to the 8th meters per second. Now notice I'm going to divide by my wavelength, which is 2.40 times 10 to the negative 5th meters. Notice what's going to happen here. My meters is going to cancel, right? Meters cancels. And then when I divide this out, my answer is going to be in seconds to the negative 1. Or per second, or we could also write it as hertz, because that's the same thing. So the other question sometimes people get here is, how do I figure out sig figs? So first of all, we do not use our speed of light as our determining factor for sig figs. Technically, constants don't count. Remember, the whole concept of significant digits is that you're rounding based on how specific your measurements are. So the thing that we measured is going to be wavelength. So if you remember how sig figs work, 2.40 has 3 significant digits. All of the digits in a number that's in scientific notation, all the digits written here count. So there's 3 significant digits in our original number, and that means there should be 3 significant digits in our answer. And so we're simply going to divide, and again, this relies on you remembering how to do this in your calculator, either with the caret or with the E or EXE button. So that's really, really important. Remember, some of your calculators are going to want you to put parentheses around this. It really depends on the calculator that you're using. So you have to know your calculator or you're going to get a lot of problems wrong in this chapter. Now, I'm going to erase my work and just put the answers up so that we can get through a little more of this, but you can always pause it, solve it yourself, and then double check your answer. So here's my formula. Here's my work. And so 3 times 10 to the 8th meters per second divided by 2.4 times 10 to the negative 5th meters is going to give me 1.25 times 10 to the 13th seconds to the negative 1, or you could just say hertz. So that's a sample problem. Now there are 2 more problems here. What is the frequency of radiation whose wavelength is 6.25 times 10 to the negative 3 meters? And a laser has a wavelength of light that is 670 nanometers. What is the frequency of the radiation? So in this case, you're going to have to convert nanometers to meters before you plug into the formula. So I'm going to pause. If you want to try to solve it, pause the video here. And then I'm just going to give you the answers so we can move on. So our first one, the correct answer should be 4.80 times 10 to the 10th seconds to the negative 1, or hertz. And then our second one should be 4.5 times 10 to the 14th seconds to the negative 1. Now, in another slide, we're actually going to go over how to do these conversions, but I'll do a quick walkthrough right now. So if I need to convert this to meters, and the reason I have to do that is because my wavelength and my frequency, my formula, remember, speed of light was in meters per second. So the only way I can't plug in 670 nanometers because that's not one of the units I'm using. I need to convert that to meters so it will appropriately plug into my formula. So to do that conversion, you would do this. 670 nanometers times, and this is called dimensional analysis. We're going to use this a lot in the upcoming chapters. So it's something you should become familiar with. I'm going to put my conversion factor here. So 1 times 10 to the 9th nanometers on the bottom is the same as 1 meter. So this is my conversion factor here. Notice the reason I'm setting it up this way, how do I know which thing goes on the top and which goes on the bottom, is I want nanometers to cancel. So now to solve this, I would do 670 divided by 1 times 10 to the 9th. And that would convert this from nanometers into meters. All right, so that's how you do the conversion factor. And again, it's on another slide in this PowerPoint, how to do those. But that's called dimensional analysis. And anytime you have to convert, this is the important thing. You want to set it up so that the unit you want to cancel is on the bottom and the unit you want to convert to is on the top. All right, so really quick. So light waves are part of what we call the electromagnetic spectrum. It is listed multiple ways. It separates the light into different frequencies and different wavelengths. Some pictures will have it from highest frequency to lowest frequency. Some have it the opposite way. I'm going to show it to you in order of highest to lowest energy. And so this is our highest to lowest energy. It's going to be gamma rays, X-rays, UV, visible light. This is the light we can see. Then infrared, microwaves, radar, and radio. These are what we can oftentimes hear, or at least radio. So here's a picture of what this looks like. So in this case, this one is showing it in order from longer wavelength to shorter wavelength. But notice here's radio waves, microwaves, infrared, visible light, UV light, X-rays, and then gamma rays. So these have the highest frequency over here, and that would also be the shortest wavelength. These have the longest wavelengths on this side, which would mean that they have a lower frequency. Bigger wavelength, lower frequency. So long wavelength, small frequency, short wavelength, high frequency. And then the visible spectrum is usually in nanometers, and you can see why, because if you do it in meters, you get these very, very tiny numbers. And so it's oftentimes measured in nanometers, but this is the spectrum of what we can see. And sometimes it's easy to remember UV comes right after violet. It's a strong light. And infrared is right below red. It's actually weaker than red light.